Welcome to this explainer. Okay, so if you've ever flipped through a chemistry textbook and just felt totally overwhelmed by massive words like stereochemistry or nucleophilic substitution, you are absolutely in the right place today. We're going to see how these intimidating concepts are literally the blueprints of our world. We'll connect these complex molecules directly to stuff you experience every single day, from life-saving medicines to huge global environmental challenges. So settle in, get comfortable, and let's unlock the secrets of haloalkanes and haloarenes. Here's our quick roadmap for today. First up, we'll meet the halogen heroes. Second, we'll step inside the umbrella reaction. Third, the mirror image mystery. Fourth is metal magic and Grignard. And finally, number 5, DDT and planet care. Let's dive right in.
Part 1. Meet the halogen heroes.
So imagine a standard hydrocarbon, just your basic everyday molecule made of carbon and hydrogen. Now, think of it like a sports team, and you're swapping out a regular player for an absolute superstar athlete. In chemistry, that superstar is a halogen atom, like chlorine, bromine, or iodine. When you replace one or more of those everyday hydrogen atoms with a halogen, you create a brand new molecule with completely new superpowers. If that original molecule was a straight carbon chain, also known as aliphatic, you get what's called a haloalkane. But if it was a closed carbon ring, an aromatic, you get a haloarene. Now, the structure here is key. In a haloalkane, the halogen hooks up to an sp3 hybridized carbon, but over in a haloarene, it attaches to an sp2 hybridized carbon. Why does that even matter? Well, that sp2 carbon in the haloarene has a greater S character. In plain English, it's more electronegative, so it actually pulls the halogen closer to it. This makes the bond shorter. And you know how a really short stick is way harder to snap over your knee than a long one? It's the exact same principle here. That shorter chemical bond makes haloarenes way less reactive and much harder to break apart than haloalkanes.
And hey, these aren't just abstract drawings on a chalkboard. These are real-life heroes. Take chloramphenicol. It's a chlorine-containing antibiotic produced by microorganisms, and it is incredibly effective at treating typhoid fever. Or look at our own bodies. We naturally produce an iodine-containing hormone called thyroxine. If you don't have enough of it, you can actually develop a disease called goiter. And then there's chloroquine, a synthetic halogen compound that's been used extensively to treat malaria. It's crazy to think about, but by simply adding a halogen to a carbon structure, we unlock chemical properties that fight some of the worst diseases in human history.
Moving on to part 2, inside the umbrella reaction. So we know these molecules are incredibly useful, right? But that brings up a really obvious question. How do they actually transform? Like, how do we take a starting molecule and turn it into something entirely different down at the atomic level? Let's zoom way in and look at a very specific race between molecules called the SN2 mechanism. The SN2 reaction happens in 3 perfectly choreographed steps. First, an incoming molecule, the nucleophile, attacks the carbon atom from the back, completely opposite to where the halogen is sitting. Second, something genuinely amazing happens. As this new bond starts forming, the old bond with the halogen begins weakening. So, for this brief, highly unstable moment, the carbon atom is actually bonded to 5 things at once. We call this the 5-atom transition state. Finally, the halogen, which chemists call the leaving group, just departs entirely, and it takes its electrons right along with it. I honestly love how our source material describes the shape change here because the nucleophile attacked from the back. The configuration of the carbon atom inverts in much the same way as an umbrella is turned inside out when caught in a strong wind. It's such a perfect visual. This is officially called the inversion of configuration. If your original molecule was shaped one way, your final product is quite literally flipped inside out. All right, section 3, the mirror image mystery. So in chemistry, molecules can actually have mirror images, just like everyday objects do. An object is considered achiral if its mirror image is totally identical and superimposable. Think of a perfect sphere or just a plain, basic coffee mug. You can place the mirror image right on top of the original and they match up perfectly. But an object is chiral if its mirror image is non-superimposable. And in chemistry, these chiral molecules are optically active, which means they interact with light in some very unique, specific ways. To really wrap our heads around this whole stereochemistry thing, let's use something you carry with you everywhere. Look at your hands right now. Go ahead, really look at them. Your left hand and your right hand are mirror images of each other. But now, try placing your left hand perfectly over your right hand, keeping both palms facing the exact same way, say facing the floor. What happens? Your thumbs are sticking out in completely opposite directions. They don't match up. Your hands are non-superimposable mirror images. They are chiral. And guess what? Molecules do this exact same thing in 3D space, which completely changes how they react with the world around them.
Okay, Section 4, Metal Magic and Grignard.
Let's pivot for a second to a pretty fun historical fact. The year is 1900. A chemist named Victor Grignard is just playing around in his lab, mixing organic halides with metals, and he happens to stumble upon a reaction so groundbreaking that it eventually wins him the Nobel Prize. So what did he do? Well, Grignard found that if you take a haloalkane and react it with magnesium metal in a solvent called dry ether, you create an entirely new class of chemical helpers known as Grignard reagents. These are organometallic compounds. And what makes them absolutely game-changing is that they contain a direct bond between a carbon atom and a metal atom, magnesium in this case. This carbon-metal bond turns the Grignard reagent into an incredibly powerful tool, letting chemists easily build much larger, way more complex molecules. It is literally chemical magic.
Which brings us to our final section, Part 5, DDT and planet care.
Now, the history of DDT is honestly one of the most dramatic timelines in modern chemistry. It's a polyhalogen compound that was first prepared way back in 1873. But it wasn't until 1939 that a guy named Paul Muller discovered it was an incredibly effective insecticide. I mean, it was so good at killing malaria-carrying mosquitoes and typhus-carrying lice that Muller actually won the Nobel Prize for it in 1948. After World War II, its use just exploded globally. But check out the end of this timeline. By 1973, only 25 years after that Nobel Prize, DDT was banned in the United States. So how on earth does a miracle chemical turn into a global environmental hazard? Well, why the ban? It's a massive cautionary tale. First off, nature fought back. Insects quickly developed a resistance to it. Second, researchers realized it was highly toxic to fish. But the absolute biggest problem came down to its chemical structure. Remember how we talked about those incredibly stable, hard-to-break bonds? DDT has those. It's remarkably stable, and it's highly soluble in fat, but not in water. This meant animals couldn't easily metabolize or excrete it. So when a small fish ate DDT, it just got stored in its fat. Then, when a bigger fish ate 10 of those small fish, it accumulated all of their DDT. This vicious cycle, called bioaccumulation, meant the chemical built up to highly dangerous levels in animal tissues all the way up the food chain. And that brings us to a final, pretty heavy question I want to leave you with today. We've seen how haloalkanes and haloarenes can do amazing things, like literally curing malaria and helping us build life-saving complex molecules. But we've also seen how polyhalogen compounds, things like DDT or freons, can persist for years and cause serious damage to our ecosystems. The chemistry itself? It's neutral. It's just nature's blueprint. So the ultimate question for you, as the next generation of informed citizens and maybe even scientists, is this: how do we balance this incredible chemical innovation with actually preserving our environment? It's a massive challenge for sure, but hey, by understanding the fundamental science we talked about today, you're already one step closer to figuring it out. Thanks so much for hanging out with me for this explainer. Keep asking great questions, and I'll catch you next time.